So hi everyone, and welcome to this fifth lecture on massive binaries. So today we have the pleasure to have Ciarán Furey, who's going to talk about core collapse supernovae and gravitational wave event in massive binaries. But before we dive into the lecture, let me introduce the speaker a bit more. So Ciarán is in second year of PhD in Armagh Observatory and Queen's University Belfast in Northern Ireland. He did his undergraduate studies in Dublin and then his master in the University of Amsterdam. And he expects to graduate in 2028. The topic of his PhD thesis is quantitative spectroscopy of very massive stars. And I would like here to take this opportunity to advertise one of his recently accepted paper, well, in 2025, which is the wind properties of O-type stars at sub-SMC metallicity. So, Gerhan, if you are ready, then the floor is yours.
Great. Thank you, Sophie. Yeah, my name is Ciarán, and I'm delighted to be given the fifth lecture of the Massive Binary Lecture Series. Until now, we've looked at how massive binaries form and evolve throughout their lives, but today I'll touch on the endpoints of massive binary evolution, namely core collapse supernovae, and when two compact objects merge, the gravitational wave events. So my lecture is outlined as follows. I'll firstly briefly recap core collapse supernovae in single stars. Then I'll motivate why we should consider binary evolution in core collapse supernovae. I'll talk about the pre-supernova binary evolution required to produce different types of stripped envelope supernovae. And I'll talk about the kicks that can be imparted on the binary system due to a supernova going off within a binary. And then I'll talk about what happens when the other star explodes and when two compact objects merge. So a star born with at least 8 solar masses can undergo core collapse at the end of its life. That's when an iron core forms in the center and nuclear burning stops, and suddenly the outward pressure due to the nuclear reactions in the core disappears, meaning the star can no longer support its own weight. Due to high temperatures and densities in the core, it does not receive enough pressure from electron degeneracy, meaning the core becomes gravitationally unstable and it collapses. The densities increase in the core so much that the strong nuclear force becomes repulsive. This produces a strong or fast outward moving shock, which is called a bounce. And this shock stalls typically at around 100 kilometers from the center. The high densities also cause a proto-neutron star to form, and the delayed neutrino emission from the production of this neutron star in the center can actually determine whether or not a successful supernova explosion actually occurs. For instance, there might be sufficient energy to revive the stalled shock front and produce a supernova explosion. Or in the case a star is very massive, it might not have enough energy to overcome the weight of the star, and then a direct collapse might occur. Now, the exact explosion mechanism is not very well understood, and it's a highly complex process because it requires detailed treatment of, general relativity and magnetohydrodynamics and neutrino transport. But whether or not a neutron star or black hole forms probably depends on how compact the core is, the compactness, which is given by the amount of mass within the radius of the core. Generally, more massive stars have more compact cores, but this might not be a monotonic function of mass. Now, depending on the supernova explosion energy and also the envelope properties of the progenitor star, what we observe can be actually quite diverse. So to this end, you've probably heard of the supernova zoo that has been established to kind of capture all this diversity we observe. So a supernova that we observe is defined by its light curve and also its spectrum and how the spectrum evolves over time. Generally, they're split into type 1s and 2s, depending on the absence or presence of hydrogen in the spectrum, respectively. A subset of type 1s, the type 1As, are believed to be thermonuclear explosions of white dwarfs, which come from low mass star formation, so we will not touch on them much in this lecture. What we'll focus on is in this blue box, the core collapse supernovae. Still the main discriminant of a core collapse supernovae is the presence or absence of hydrogen. So type 2Ps and 2Ls are hydrogen-rich core collapse supernovae. Then there are hydrogen-poor stripped envelope supernovae. Within this subcategory, there's a intermediate phase, the type 2b, which shows hydrogen, but this disappears after a couple of weeks. And then there are hydrogen-free supernovae, type 1b's and 1c's, which do and do not show helium in their spectra, respectively. Now, the presence or absence of and the type of compact object left behind post-core collapse primarily depends on the initial mass of the progenitor, the metallicity of the progenitor, and also the rotation rate. So here I'm showing the predicted compact object to be left behind as a function of initial progenitor mass and metallicity for a non-rotating single-star progenitor. Now, as I said, the core collapse mechanism is not very well understood, or the exact explosion mechanism. So for that reason, this plot is probably more complex, and even more so because I'm only showing a non-rotating progenitor here. But you can see for lower mass stars, neutron stars are predicted to be left behind post-core collapse. With increasing mass, there's more mass available to potentially fall back onto the protoneutron star post-core collapse, leading to a black hole formation by fallback of this material and a weak supernova explosion. But for very massive stars, these can collapse directly into black holes. At high metallicity, where stellar winds are strong, very massive stars have winds strong enough to sufficiently self-strip, leading to a lower core mass at core collapse. So in this case, it's predicted for very massive stars at high metallicity to produce a neutron star, while for decreasing mass and metallicity, stellar winds get weaker, so they retain more mass at core collapse, leading to a higher core mass and therefore the potential for a black hole to form. Now, as I showed previously, depending on the envelope properties, what we observe depends on the envelope properties. So yeah, for high mass and metallicity, these stars can strip their outer envelopes themselves. So in theory, these can produce these hydrogen-free type 1bc supernovae. While for decreasing metallicity and mass, stellar winds are weaker, so they retain more of their envelope at explosion, leaving behind a more hydrogen-rich core collapse supernova. Now I want to take a moment to talk about this transition from 2p to 1bc a bit more, because this will become significant when we start to talk about binary evolution. Yeah, so still within the core collapse supernovae corner of the supernova zoo, yeah, the main discriminant is the amount of hydrogen and helium in the envelope. So type 2p supernovae show a very particular plateau phase in their light curves, and they are also very rich in hydrogen and helium. Type 2Ls are hydrogen rich, but they do not show this plateau phase in their light curve. And yet type 2Bs are this intermediate phase, which show hydrogen in their spectra, but this disappears after some time, and this is indicative of a very minimal amount of hydrogen in the envelope. While type 1Bs and Cs are hydrogen free, but they have and do not have helium respectively. So now we could think, in the event that these form in a binary, we can think of this decreasing hydrogen level as a degree of increased stripping, right? If more mass is transferred in a binary, there will be less and less hydrogen left of the progenitor. So we will expect for more mass transfer to see less hydrogen in their spectra. And keep this in mind for when we talk about pre-supernova evolution. But first, why should we even bother considering binarity in core collapse supernovae? Long story short, they tend to pop up in the different regions of the supernova zoo. Very briefly, supernovae of type 1a are believed to be thermonuclear explosions of accreting white dwarfs. So in that sense, binarity is likely involved there. But the exact explosion mechanism is unclear. Even hydrogen-rich type 2 supernovae, which are commonly associated with single-star evolution, sometimes they can show evidence of binarity in the progenitors. A famous example is 1987A, one of the most well-studied supernovae because it went off nearby in the Large Magellanic Cloud. Even this one shows evidence for a binary progenitor. For instance, it was a blue supergiant as it exploded, as opposed to a red supergiant, which is what would normally be predicted from single-star stellar evolution. It shows anomalous chemical abundance patterns in its photosphere and also the circumstellar material, which have been suggested to have gotten there by non-standard mixing means. And it also, when you zoom in, it has this characteristic axisymmetric ring structure as opposed to a more, spherically shell-like ejecta. And all of this points to, or favors, either accretion during the pre-supernova phase or even a merger. progenitor. But the subtype of core collapse supernovae, where binarity most likely plays the most significant role, is within the stripped envelope supernovae, so type 2Bs and 1BCs. So when we have a massive star, we can think of two different ways it can produce a stripped envelope supernova. So for very massive stars, stellar winds are very strong, so they have winds strong enough to self-strip. So in theory, very massive stars can form stripped envelope supernovae in isolation. But for these low mass massive stars, if you will, 30, 25 solar masses and below, they do not have winds strong enough to strip themselves. So the only way these can produce stripped envelope supernovae is through binary interaction. And also observations show evidence for binarity in the production of stripped envelope supernovae. And a famous example is IPTF 13BVN, which is a type 1b supernova. To reproduce its light curve, a low mass stripped helium star progenitor was required. And that is what you're seeing here, as opposed to a more massive stripped helium star, which would be a Wolf-Rayet star, which would form more from more massive progenitors. And not only this, but an interacting binary can self-consistently reproduce the observed lack of hydrogen in the spectrum of this supernova, and also the pre-supernova photometry of the progenitor candidate. Looking to larger samples, a later study analyzed 80 such stripped envelope supernovae and found that for all of them across all subtypes, relatively low ejecta masses of around 3 solar masses. And from this, they suggested that the progenitor for all these different subtypes were of similar in nature, of similar mass. They suggested that the progenitors could be on the low mass end to produce this sort of ejecta mass. And from this, they concluded that the binary channel of producing stripped envelope supernovae is favored. So in that sense, yeah, observations do show evidence of binarity in these stripped envelope supernovae. So yeah, we motivated why we should consider binarity in the production of core collapse supernovae. So let's talk about the pre-supernova evolution required to produce the different progenitors and types of stripped envelope supernovae. So the main thing that governs the type of progenitor and supernova we see within a binary system depends on the initial mass ratio of the system, as well as the initial separation of the two components. Today, I'll only focus on the effect of the initial separation between the two components of the binary. So what I will show is the evolution of a donor star within a binary system with a fixed mass ratio across the Hertzsprung-Russell diagram. So in this case, it will be an 11 solar mass, giving mass to a 9.9 solar mass object at LMC metallicity. So just to explain the different points through this evolution, the green point is where core hydrogen burning ends, the yellow point is where core helium burning starts, and the red point is the point of core helium exhaustion. And the thick green line is the mass transfer episode. In all cases, case B mass transfer is required, or case C, which is mass transfer after the exhaustion of core hydrogen. So on the Hertzsprung gap on a thermal timescale. So yeah, I'll look at the effect of changing the initial period or initial separation on the production of stripped envelope supernovae. And we can also think of this as the time of the onset of mass transfer, right? Because in tighter systems, the Roche lobes are smaller. And you can think of this from the standard Eggleton formula that describes the Roche lobe size. And because in a tighter orbit, Roche lobes are smaller, in this case B scenario, where the star is expanding, it will soon after the beginning of its expansion will fill its Roche lobe and begin transferring mass. While in a wider orbit, the Roche lobes are larger, so it will transfer mass later. And also the degree of expansion dictates the envelope properties, so whether it is radiative or convective, and therefore its response to mass transfer. So this initial separation in turn dictates the post-mass transfer as well in that sense. So yeah, in this scenario, it's a relatively tight orbit of 10-day period. So the donor star transfers mass soon after it begins its journey across the Hertzsprung gap. Because it quickly fills its Roche lobe, it loses mass quickly, so it drops in temperature and luminosity. But once the helium-rich layers are revealed, it increases in luminosity again. Then once mass transfer ends and core helium burning starts, in this scenario, it contracts to restore thermal equilibrium. And because it's not fully stripped in this sense, or in this example, there's still a little envelope on top of the exhausted helium core, so it expands after core helium burning. But in this case, it explodes as a relatively hot blue supergiant progenitor. But looking at a wider orbit, the star can expand more, and in this case, it can complete its journey across the Hertzsprung gap, and it will start transferring mass, in this case, as a very much inflated red supergiant with a deep convective envelope. So the post-mass transfer evolution, in this case, dictates a blue loop evolution, but again, it goes back red and explodes as a cool red supergiant. So the key takeaway of this effect of initial separation is that in a tighter orbit, mass transfer happens earlier, while in a wider orbit, it can happen later. And this dictates the degree of stripping, so how much envelope is stripped, and therefore the observed progenitor and supernova type. So when one does a population study of different binary configurations for different initial periods, and also initial donor masses, we can get an idea of what we might expect to see in reality. So you can see this is showing log initial period on the x-axis and initial donor mass on the y for LMC metallicity. And we can see that, for all the wide orbits, they explode as red supergiants because they are allowed to expand and fill their Roche lobe. They're allowed to expand more before they fill their Roche lobe. But for tighter periods and tighter orbits, they can expand less and less than what they want to. And they explode as hotter progenitors, but still with hydrogen present, so 2Bs in this case. But for more massive stars in this tight orbit configuration, they have winds strong enough to strip away the remaining envelope that's left behind post-mass transfer. And because these winds are a key aspect in governing how much they strip, it's always telling when doing these sorts of studies to look at the effect of different metallicity. So this is now looking at solar metallicity, so higher, where radiative-driven winds are stronger. And the main difference is that in these tight orbit configurations, the hot 2B progenitors are replaced with just hydrogen-free 1Bs because the winds are stronger in this case, so they can strip away the remaining envelope. So yeah, in these studies, the wind prescriptions used are probably the main uncertainty, especially in the later phases of evolution. So in the red supergiant phase, or potentially when they're hot, the Wolf-Rayet prescription used, because winds are very much enhanced here, and it determines whether or not the envelope is stripped or not. So now we talked about the evolution that leads up to the supernova explosion, what the progenitor is, and what type of supernova we expect to see. But now let's talk about what happens when a star actually explodes and discuss the fate of the system. Will it unbind? Will it remain bound? Can we tell from observations? So in that sense, we're going to talk about supernova kick mechanism. So to learn about the fate of the system, we'll consider the following setup. So at the time of explosion of one of the stars in the system, the orbit will be circular. The explosion will be instantaneous and symmetric. And as a result of the explosion, an amount of mass we'll call delta M here will be lost from the binary system. And the question we want to ask, what is the eccentricity of the new orbit post-supernova? So because it's instantaneous, we can say that the position at the time of explosion will be equal to the periastron position of the new orbit, which has an eccentricity E. Also, the velocity at the point of explosion, the orbital velocity at the point of explosion will be equal to the periastron velocity of the new orbit, again with eccentricity E. And if you want to brush up on how to mathematically describe a binary system, refer you back to lecture 1, Jonathan's lecture. So here we can substitute in the periastron position with the relation above. And from here we can rather trivially solve for the eccentricity of the new orbit. Okay, well now we can start to ask an interesting question. This system will become unbound when the eccentricity is greater than 1, or equivalently, letting it equal 1 and solving. In this setup we have considered a circular orbit with an instantaneous symmetric explosion. It will become unbound when at least half of the total mass of the system is lost from the supernova. So yeah, in that sense, the fate of the system is largely determined by the mass loss from the supernova. We can also do conservation of momentum of the system before and after to see what will be the imparted velocity kick, systemic kick velocity on the system due to this sudden mass loss, which I'd show without derivation. But we can see that for lower and lower mass lost, we expect to see a lower kick velocity imparted on the system. And we do see such systems consisting of a compact object that is formed from core collapse and an O star. Probably the most famous example is Cygnus X1, which is a high mass X-ray binary consisting of an 09.7 supergiant and a black hole. This has from proper motion on the sky and I guess interferometry, a systemic velocity of around 10 kilometers per second has been measured for this system, which is relatively low. And its motion in the sky is also consistent with the motion of its host association, Cygnus OB3. So what this plot is showing all the members from Cygnus OB3 along with Cygnus X1. And the arrows dictate the arrows give the distance traveled within the last 500,000 years. So because it shows a low systemic velocity and it's consistent with the motion of its host system, by looking at it, the kick velocity imparted due to core collapse, we can it is understood now that this system has formed by direct collapse because it has no kick, so minimal mass was lost during the supernova. We can also look at X-ray quiet systems, so non-accreting black holes within the orbit. So a famous example of this is VFTS 243 in the Large Magellanic Cloud. So this system has a near circular orbit, so low eccentricity, and if you remember from our estimation from our system, the derived expression for eccentricity, we can infer that minimal mass was probably lost during the production of this black hole. When considered along with its neighboring stars in the sky, its proper and radial motion are consistent with these, so this suggests no kick was imparted, or a minimal kick was imparted during the production of the black hole. And also, the rotation period of the O star differs from the orbital period of the system. So this means that tides have not yet erased the information, the pre-supernova configuration of the system. So in that sense, these X-ray quiet systems are pristine laboratories, not only for massive binary physics, but also for the physics of supernovae as well. So we talked about black holes within Cygnus X1 and VFTS 243. But neutron stars are quite different because in the production of neutron stars, we expect a successful supernova to have happened, so a large amount of mass loss from the system very suddenly. And also because these core collapse explosions are very complex and asymmetric, and so we expect the system not only to acquire a kick velocity due to mass loss, but the neutron star itself due to asymmetric mass ejection. So by conservation of momentum between the neutron star and the mass ejected, you can get an idea of the magnitude of the kick to be imparted on the neutron star. So here I show an example of such a formulation. So this is of Janka 2017. I show without derivation, but if you want to look for more details, I do recommend this source. So by considering, conservation of momentum between the neutron star and the ejecta, and typical explosion and ejecta explosion energies and ejecta masses, you can see that neutron stars are likely receive kicks of the order of hundreds of kilometers per second, as opposed to 10 kilometers per second we saw with Cygnus X1. So it shows indeed for more energetic explosions and more mass ejected, and a lighter neutron star would expect a stronger kick to be imparted on the neutron star. Within this formulation, this parameter F was introduced to describe the fraction of the total explosion energy that goes into the kinetic energy of the ejecta responsible for kicking the neutron star. So more energetic ejecta, more of a kick on the neutron star. But one of the key parameters is this asymmetry parameter. So it's the volume integral of the momentum of the ejecta compared to the total momentum of the ejecta. So this just says, if it's a completely symmetric explosion, this directional integral is zero. So yes, that means no kick will be imparted on the neutron star during the production of during its production. But the more asymmetric the explosion is, the larger the kick. And you can think of it just, the more the mass goes one way, the more the neutron star goes the other way, just by conservation of momentum. And we do indeed see neutron stars moving at high velocities in space. So this is showing the motion of pulsars within the galactic plane. So there's different longitudes and different heights from the galactic plane. So this is different pulsars, so rotating neutron stars. Each point is a pulsar, and each line from each point dictates its velocity through space. And when you do a study on a full sample of these, it's found that indeed they are moving at hundreds of kilometers per second. So this is, I guess, the 3D speed and log space, and also the probability density. So we see that most of them are moving at hundreds of kilometers per second, some even at thousands of kilometers per second. So this all favors asymmetric explosions and also large amounts of mass loss from the supernova. But in the event they form in binaries, because they receive such large kicks, so much mass is lost. We can expect from our previous formulation that when neutron stars form, the system can likely be unbound because of these high kicks. So in this sense, understanding or analyzing the kick velocities, we can learn about the pre-supernova configuration. So we talked about what happens when one star explodes, but what about when the other star explodes, if they're both massive stars, if it leaves behind a compact object and the system remains bound? What happens when they merge, and how do we describe the gravitational wave radiation it produces? So when talking about gravitational waves, it's always useful to begin with this plot, so the masses in the stellar graveyard, and I'll take a moment to explain what we're seeing, because it's always useful to look at it, especially when the latest catalogs are released. So each point on this plot represents a compact object, either a neutron star or a black hole, and whose mass is given by its position, its vertical position. The yellow and orange points are neutron stars, discovered either through electromagnetic or gravitational radiation. And similarly, the red and blue points are black holes, discovered either through electromagnetic or gravitational radiation. The objects discovered by means of gravitational waves are represented on an arrow. There's 3 points on each arrow, where the 2 lower points are the masses of the objects that merged to produce an object whose mass is given by the point on the top of the arrow. And the more one looks at this, the more one can unpack. It's a very useful visualization. So, for instance, the masses of neutron stars, both from electromagnetic and gravitational radiation, are consistent with this theoretical upper mass limit of between 2 and 3 solar masses for neutron stars. But I think the most glaring feature is just the abundance of blue points, right? So the majority of gravitational wave events we observe are black hole mergers, which, we just discussed the kick velocities neutron stars can get at their formation. So this isn't surprising, right? Because the majority of systems in which a neutron star forms can be unbound very easily due to these high velocities. So for this next section, we'll mainly focus on just merging black holes. First, I want to talk about kind of what we're actually measuring during these gravitational wave events, just to get everyone on kind of a baseline so we can understand future gravitational wave events. So what we are measuring is the strain of space-time as the gravitational wave passes through our detector. It's given by this sum of the different polarizations of the gravitational wave. And I show without derivation what determines the strength or the magnitude of this strain. I think the mathematical details are not the point of this lecture. I'll show the stuff we're interested in, namely what determines them, but I point to various references if you are interested in following this up. So for a strong signal, it's favored by a tighter orbit, Here it's normalized to 1 hour, but in reality, what we're sensitive to is the in spiral at the later phase. Similar to electromagnetic radiation, I guess closer by sources are louder, if you will. But unlike electromagnetic radiation, this is a key point, it goes with simply just 1 over distance as opposed to 1 over distance squared. And this is, well, huge because any slight upgrades to our current detectors, which are given by these shaded regions, so they'd be called O4, O5, A hash. So any upgrades to our current detectors will open up a huge volume of space unseen before, and especially when new observatories come online. This 1/d dependence helps us because it opens up a vast new region of space. The strain is also proportional to this quantity called the Chirp mass, cursive M. I want to take a bit more time to talk about the Chirp mass and what it is, because it's a commonly used phrase within gravitational wave astrophysics. So it's given by the product of the reduced mass of the system with the total mass of the system to these respective exponents, and written out explicitly, it's given by this for a system of two components, M1, M2. If you remember, the strain is proportional to the Chirp mass to the 5/3. So this means that both high mass, well, systems with two high mass components and systems with two components at similar masses produce a stronger gravitational wave strain. And this is what I'm trying to show here. So for a system of M1 and M2, the Chirp mass of the system is given by the color, and you can see that not only more massive, but also more massive, and primary and secondaries give a higher Chirp mass. So why is this quantity commonly used in the field? Well, essentially, it's one of the most directly measurable quantities. Because for a gravitational wave with frequency f GW, the time evolution of the gravitational wave we are observing due to the in-spiral is governed by the Chirp mass to the 5/3 here. So when we see these detections, um, the gravitational strain as a function of time, we see that during the in-spiral, the frequency gets larger and larger as the peaks get shorter and shorter. And then they merge, and then we see this decay phase. But during this in-spiral phase, the frequency evolution of this wave is governed by the Chirp mass. So in that sense, it's one of the more directly measurable quantities. But in reality, because it's a wave stretched over the expansion of the universe, we measure the Chirp mass times the redshift. Indeed, yeah, as I said, the Chirp mass is generally one of the more well-constrained quantities. For example, the double neutron star event 170817. The Chirp mass in the source frame was constrained to within 0.5% or within 1% precision. But what we're interested in is the component masses, right? Because that's what we're predicting from our binary evolution modeling. In reality, this waveform we observe is a function of many different parameters. So not only the Chirp mass, the mass ratio, the position on the sky relative to the orientation of the observatory, various spin parameters of the compact objects, as well as descriptions of, say, the noise of the detector and so on. So it can get quite complex. So for that reason, sophisticated statistical inference is performed to get the component masses from the measured Chirp mass. And for kind of the seminal paper on how this is done, I refer you to Veitch 2015 if you want to see more about how this is done. And not only that, there's different waveform models that assume maybe spinning components or non-spinning components. So the final quoted component masses, they are typically kind of combinations of all these different waveform models. So here I'm showing a posterior for the primary and secondary mass within quite a massive black hole merger event that was on the archive recently. And what I want to show here is that while the Chirp mass is most often well constrained, sometimes there can be quite large uncertainties on the inferred component masses. So bear that in mind. So when one does this inference on an entire catalog of mergers, we can start to plot distributions and see if there's any structure in them. So this is the latest release of the gravitational wave transient catalog 4.0, which consists of 153 binary black hole mergers at a redshift of 0.2. And what this is showing is as a function of primary mass, the merger rate of a system with this primary mass per unit co-moving volume per unit source time. And when we check the distributions, we can look for interesting structure. So this is showing 3 different lines. So the black is a fit to the previous release of the gravitational wave transient catalog, while the red while the orange and blue lines are fits to the most recent gravitational wave transient catalog. We can see that there's still this there's a 35 solar mass bump found in both versions of the catalog, but interestingly, in the most recent release of the gravitational wave transient catalog, it is found that there's significantly more mergers at 10 solar masses, and it's significantly different to the previous what was found previously. So now what we're interested in is what determines the different structure that we observe. How can massive binary evolution determine this? So yeah, what systems are responsible for this event? So to do this, we will consider the orbital separation, the evolution of the orbital separation as a function of time, purely due to gravitational wave radiation in a circular orbit. Again, I show without derivation the formula, but for the seminal paper is Peters 1964. So this is showing the rate of change of the orbital separation with time, and it's given by the product of these constants times the component masses, M1, M2, and the reduced mass of the system divided by the separation cubed. And there are other eccentricity terms, but we will not consider them as it's a purely circular orbit here. In these sources, you might see that all the masses and the constants are lumped into this parameter called beta. So here we have a rather trivial differential equation, right? Because you bring the a to one side, dt to the other side, do some integration, and we can actually derive an expression of the orbital separation as a function of time, and it's given by this 1/4 power law. And when plotted out as a function of time from the time of birth to merging time, you see it's a slow in spiral, but as it gets closer and closer, they quickly merge. So we have a key constraint, right? The systems we observe need to have merged within a Hubble time, right? Because we're observing them now. So we have this constraint. So at the Hubble time, the separation is 0. So when evaluating the various constants and assuming a circular orbit of equal mass components, we can ask the question, what separation must they be born at to merge within a Hubble time? So that's what I'm showing here. And plotted out as a function of component masses, we can see that the more massive the system, the further away it can be born. But looking at the vertical axis, it's not that they can't be born far away, right? It's still within an AU for 125 solar masses. Just putting some numbers. Two solar mass components must be born within 6 solar radii in order to merge within a Hubble time. And 250 solar mass components need to be formed at a mere 0.3 AU in order to merge within a Hubble time. So we have this constraint for our models, for our predictions. Tight systems have to be formed. It's just no way about it. So now we can discuss the different pathways that might lead to the production of a tight system of 2 compact objects. One of them is the common envelope evolution channel. If you want to hear all about that, the previous lecture by Yasmin perfectly covered it. But the idea is during the common envelope phase, friction can release energy and shrink the orbit. So by the time 2 compact objects form, they will be close together. There's also the stable mass transfer phase. If you want to hear about mass transfer and stability and instability, I refer you to Dwight Bian's lecture. The idea is depending on the initial mass ratio and the degree of how conservative the mass transfer is, they can be born relatively tight and avoid merging until the production of the two compact objects. There's also another channel, the chemically homogeneously evolving channel. So what this states is that two stars can be born tight, and if they're rapidly rotating, the degree of internal mixing within the stars can be so much that they can be completely chemically homogeneous. Now, the catch with chemically homogeneous stars is that they do not expand on the main sequence. Rather, they contract a little bit. So that means if two chemically homogeneously evolving stars are born tight, they can stay in a tight orbit as they evolve because they don't expand and fill their Roche lobe and transfer mass. So this favors rapidly rotating stars, but also low metallicity because the winds are weaker in this regime, and that means at weaker winds, they lose less angular momentum, so they can stay rotating fast for longer. And for completeness, there's another channel by means of dynamical interactions to produce merging black holes, where in, say, a globular cluster, for example, the more massive components can gravitationally settle to the center, where they have a higher chance of interacting. But when we discuss binary black hole formation, it's always useful to consider the uncertainties involved in our predictions. So because we're observing merging compact objects at the Hubble time, and they take quite a while to merge, so in principle, we're probing stars that form very early on in the universe. So we need to understand how stars form at low metallicity in the early universe, but also the star formation rate as a function of redshift. Again, because they're low metallicity stars, we need to understand stellar evolution at low metallicity. And the winds are key in determining their evolution. So how the role of metallicity in their stellar winds, for example. The mass transfer is a complex three-dimensional hydrodynamical process, which is parameterized in 1D in our current codes. So this is a degree of uncertainty. If you attended last week, you saw that common envelope evolution is parameterized by alpha and lambda, which can vary by orders of magnitude. And so this is an uncertainty. And also the core collapse mechanism itself, like when will it collapse directly into a black hole, or when will it produce a neutron star? And depending on the uncertainties or on the assumptions one makes in making a prediction of black hole merger rates, there can be orders of magnitude uncertainty. So what this plot is showing is a number of different studies predicting local black hole merger rates, but each study has their own assumptions. So these green points are just for binary evolution. There's the chemically homogeneously evolving channel, merging population 3 stars, triple systems, or even higher order multiples, and so on. But the key here is that depending on the assumptions you make, there can be 8 orders of magnitude difference in the prediction. But not all is doom and gloom. There's currently a lot of work happening to further understand these aspects. So there's large-scale observational campaigns to understand evolution at low metallicity. For example, Bloom, binarity at low metallicity, is looking at the binary properties in the small Magellanic Cloud, which is at about a 5th solar metallicity. So they're looking to see the role of binarity at lower and lower metallicity. And X-shooting Ulysses is looking to understand the role of metallicity in radiation-driven winds from stars in the LMC and SMC. Not only observationally, but there's hundreds of research groups pioneering our theoretical understanding of binary evolution worldwide. And also, due to this 1/d dependence, future observatories and upgrades to current ones will observe more and more events, especially in space where larger baselines are available. So these will be able to probe completely different regions of parameter space, so at lower frequency events. So we'll have more observations to work with. So that brings me to the end of my lecture, where I'll briefly conclude. At the start, we talked about core collapse supernovae and single stars. A highly complex process, depends on the initial mass, rotation, and metallicity, and the type we observe depends a lot on the envelope mass and composition. Showed binaries kind of show up in the different regions of the supernova zoo, so it's important that we consider this channel in the production of core collapse supernovae. We saw that case B transfer is favored in the production of stripped envelope supernovae in a binary, and the progenitor type and supernova type is highly dependent on the initial mass ratio and period. Supernova kicks can be useful for constraining the pre-supernova binary configuration, and the fate of the system largely depends on how much mass is lost during the core collapse supernova, and also the asymmetry of the explosion. And finally, mergers and gravitational waves, a completely new branch of astrophysics that probes the endpoints of the first stars, but it's still very much uncertain. And with that, I'd like to thank you very much for your attention.
Thank you very much, Ciarán, for this fantastic lecture. Um, do we have questions for him in the audience? Please raise up your hand. Yeah, Luca, please go ahead. No? Okay, in the meantime, because nobody has a question yet, I have a question, more out of curiosity, but you discussed the case, page 14, that the orbit is initially circular, but what happens if the orbit is not circular at the beginning?
If it's not circular, then I guess I'll have to think a bit about that.
I'm not sure it's an easy question. I just wonder if
I guess I guess I guess the assumptions we make won't be valid, and the assumptions in saying that the position will be directly equal to the periastron position of the new orbit. So likely these assumptions won't be made.
well, I was wondering, for instance, if the kick happens when it's a periastron and apastron, how it might affect the fact that the system is unbound at the end or not.
Yeah, that's a good question. Um, but unfortunately, I can't give you a.
Okay, I will stop bothering you with my question then.
Yeah.
Sorry. Okay, Gloria, you have a question, please go ahead.
Thank you, Sophie, and thank you, Ciarán. And actually, my question has to do with what Sophie just asked. All the models assume what Chris Tout a long time ago said in one of his papers. Binary stars evolve as single stars until one of them gets in the way of the other. And one getting into the way of the other means Roche-Loeb overflow, basically, in most models. So the problem is that if you have an eccentric orbit, the stars are getting in each other's way from the very beginning during the entire orbital process, because you cannot have a synchronously rotating star in an eccentric binary. So you have acceleration, you have tidal flows, and this somehow must affect the evolution of the star, even starting from the main sequence, if the stars are born as eccentric binaries. So I'm just wondering if you have any thoughts on this, or if any work is being done in terms of precisely what the final products may be and what the mixing efficiency might be when you have such a non-equilibrium binary system as many systems may be.
Yeah, thank you for your question. It's definitely very interesting, but unfortunately, I don't have the expertise in the field. But I could maybe open up if someone has a point or something to say. Yeah, but unfortunately, I'm unaware of work that's being done. But
So
maybe,
don't you think, I mean, my question is it relevant, right? Because if nobody's really working on this problem, maybe it isn't relevant. Maybe stars do evolve as single stars until they start the Roche-Loeb overflow. And so everything is fine, but maybe not. And so that's, I think, the question we have to be asking.
okay.
If I can jump on it, it is so To my opinion, we cannot consider binary stars, especially on short orbit, to behave simply as single stars. But I think there are people here in the audience that are maybe a bit even more experts. So Luca, for instance, if you're still here. You're muted.
Can you hear me?
Yes.
So I was about to react actually about Gloria's point. I think there is a recent paper by a student of Sylvia Tonen who touched the question of eccentric orbits and like potentially eccentric mass transfer in these orbits. And I think there are like different configurations depending on the eccentricity and separation. And you can have like continuous mass transfer or only at periastron. So that can be something. I don't think they touch the question of mixing in these systems. Otherwise, yes, of course, I think Sophia had in mind more all of the tidal interactions that can be occurring, but I don't think that there are many studies of these like tidal interaction and mixing in eccentric orbits, to my knowledge at least.
Thank you. Does that answer a bit, Gloria, or do you want to make a comment back?
Well, it just says that not many people are working on this problem, but it does not answer my question as to whether it's relevant or not, the fact that a star is in an eccentric orbit or even a circular orbit where it's rotating faster than the orbital velocity, a non-equilibrium system. So, I mean, maybe stars evolved from the very beginning tidally locked. And if they reach the zero-age main sequence tidally locked, then everything will proceed as models currently predict. But what if they do not reach the main sequence tidally locked? Then what happens?
Michael, you want to react on that?
Yeah, kind of. So it is kind of what you're saying, but I think it's important to kind of point out that, I mean, when we look at the single star evolutionary tracks, the way the rotation behaves if you consider a star by itself versus the way that rotation behaves if you're in a close binary system can change quite a bit, you know? So whether or not you maintain your fast rotation because you're in a binary and tidal locking maintains your fast rotation, or if you're, again, as you mentioned, if your initial rotation is faster than whatever the synchronous rotation is and you spin down the star faster than you would otherwise expect. So I mean, in that sense, I think it's difficult to even in a binary system that hasn't reached Roche-low overflow yet, to consider these as single stars when you consider how the rotation evolves. So, I mean, maybe if you look at individual snapshots, you can still kind of think of it as single stars. But I mean, the overall, especially just the rotational evolution of the star, I think is going to be quite different. So, yeah.
Okay, thank you. Gloria, I don't know if you want to react.
Oh, thank you. I think we have we've gotten the point here across.
Okay, thank you. Do we have other question, other discussion? No questions? Okay, then I think if no questions anymore, last chance. I think we can thank the speaker again, and we meet not next week, but a week after for the sixth lecture. So thank you.
Thank you.